So in the last video we looked at why e to the theta I will rotate around in a circle depending on your value of theta. Just to recap, here we're just going to use theta equals 1 for simplicity. But we've reformatted the way we wrote our binomial. We made it into a complex number inside of these brackets. We did 1 plus 1 over n times I and then to the nth power. So this is basically a complex number. And just to refresh how complex numbers work, if it's on the unit circle, it will rotate around the unit circle when you raise it to a power. How much around the unit circle it goes depends on this initial angle here. Like this is a 45-degree angle. This complex number is actually radical 2 plus radical 2i. And if I were to raise that to the 8th power, it's going to rotate 45 degrees for each power here. So it's going to go 45, 45, 45, and it's going to rotate all the way around until we're at 1 again. So why does this matter? How does this relate to our e to the theta I? Well, as n gets sufficiently large, it's technically approaching infinity to make e. I'm not going to use infinity because that's sort of hard for people to visualize and think of. But in this case, we're just using a really ridiculously high number, and it's 1 over 10,000 here. So n is going to be 10,000. So we have a very small imaginary portion, and what this is going to do is it's going to, as n goes higher, it approaches 1, and that puts us on the unit circle. So here, this whole binomial here is going to stay on the unit circle when we raise it to a power. Secondly, the angle that this forms is very shallow. It's a very small angle, and it's going to be repeated 10,000 times here. So that is going to approximate a circle very well, because you're going to start maybe, just to overwrite here, you're going to start, basically it's going to be indistinguishable from the x-axis. You're going to start a smidgen above this x-axis, and it's going to rotate 10,000 times. So you're going to basically have these just slowly rotating, and it's going to follow that circle almost exactly. And as n goes to infinity, it will follow that circle exactly, because there's not going to be any difference between each little increment here and the unit circle, basically. And eventually, after you rotate that tiny angle 10,000 times, you're going to end up here. But we're going to go into why. We're going to go into why does pi get you all the way around to -1. We're going to start with a review on the Veritasium video. I'm going to load that up really quick here. So in the Veritasium video on how we used to calculate pi, it showed how we historically estimated its value. Now, essentially, we would approximate the circle with a polygon, and then calculate the perimeter. Now, with 6 sides, this approximation is not very good. If we increase the number of sides to 12, and you could see here as it goes around the circle here, the perimeter is getting relatively close to the circumference of the circle. And if we increase that even more, it gets closer and closer until you can't really tell the difference between the polygon and the circle. So they would use this, and they would keep increasing the sides to get this value of pi more and more accurate. So how does this help us understand our e to the theta I? Well, if we were to start at a point like radical 2 over 2 plus radical 2 over 2i and raise that to a power, we would get a very poor approximation of the circle. However, we are not starting there. We are actually starting at the very right edge of the unit circle, right above 1 plus 0i, which is right here at the bottom right, if you can see that. It's going to be a very, very small angle, which means you're going to get very small rotations. So if we were to connect each point we hit, here to here to here, you're going to make a polygon that very closely approximates the circle. And the higher value of n in our polynomial, the closer and closer you get. So essentially, zoom out here, see how small of an angle this really is. I'll just hit home. And it's basically indistinguishable from a horizontal line. And it's going to make these tiny little increments and move right along this unit circle here. So using some basic measurements, we can see exactly how far we travel around the circle when we raise e to the theta I using a binomial like this. Now, if we had something instead like radical 2 over 2 plus radical 2 over 2i, the geometry is a bit more involved. Here we can see how the height, which is the y value of this point right here, has very little to do with the distance we've gone from 1, 0, and both have very little to do with the distance in the arc. Now, you can absolutely figure this out using geometry, but it requires a little bit of work. What we need to do, though, is much simpler, thankfully. And here we could see an example with a much smaller angle, and you could sort of see what happens to all of these things. That the height and the y value, the distance to this point from 1, 0, and the arc are starting to converge. They're starting to become equal. And as you'll see, when we get straight down to it, when we get to some crazy value like 1/1,000,000th I, this circle looks like this is the unit circle is blue section here. You can't tell the difference from this point and the arc. You can't tell the difference from the height and the distance from 1, 0. They all are exactly the same. The closer you get, the more identical they will become. There's still a little bit of difference at this point, but visually you can't even see it anymore. So that's what's happening here, and that makes the geometry really easy. So let's take a look and see what happens when we start to rotate from our starting point here, and it's basically 1 plus 1/10,000th I, which is right here. 1, 0 would be here. Again, this is a very small angle, and it's going to rotate in even increments. And it's going to, whatever this rotation was, whatever this arc was, it's going to rotate exactly the same amount from here to here. It's going to go from here to here. And as you can see, this blue line again is perfectly vertical, it looks like. So this is going to make things very easy. Now, just a reminder, we chose 1 for theta. It doesn't have to be 1. We chose that for simplicity. You're going to see why it makes this part very easy. And we've just chosen a sufficiently large number. 10,000 is not infinity. E is supposed to go to infinity. However, that's very hard to visualize. You can't make diagrams on infinitesimal numbers. So just keep that in mind. This is still a very crude approximation compared to higher values of n, but it's going to be good enough. And again, this is your unit circle right here in this diagram. This blue line is poorly drawn, and these points are basically on that unit circle. So every time we rotate, they're going to stick on that, and it's going to rotate in the same arc. But since it's supposed to be a vertical line, more or less, each of these rotations are going to be whatever this height is here. So this is 1 plus 1/10,000th I. So we're going to rotate this same amount, because this vertical distance that we're at now, this 1/10,000th I, that's the same that we're rotating in the arc. So now we know the value that we're rotating in the arc. It's basically 1/10,000th I, and we're going to do that 10,000 times. So after one rotation, we're going to be at 2/10,000th I, and then after another rotation, we're going to be at 3/10,000th I. And the point to know is that the distance between these things, because again we're approximating a circle, is going to be 1/10,000th I, or 1/10,000th, just as a raw distance. And even as the circle curves, and this is not going vertically anymore, it's still going to be 1/10,000th of a distance between these 2 points. So let's pretend we were going vertically. All right, so you saw how when we were very close to 1, we basically are going vertical. So let's pretend we kept going in that direction. What if we went up 1/10,000th I 10,000 times? Well, that's pretty easy arithmetic, right? Or multiplication. This 10,000 times is just going to be up 1i. So this is going to have a distance from here to here of 1. Now, we're not going straight up, though. We're going around the circle. We're going around the circle a distance, or an arc distance, of 1. Now, the radius is 1. So we've gone 1 radian. So, as you can see here, whatever number we choose for theta, that's how many radians we are traveling. Now, again, we didn't have to use 1, but I hope it's very clear, because if this was a different number, I think it would convolute the idea a little bit. But we're going up 1/10,000th I 10,000 times. We might as well have been going up 2/10,000th I 10,000 times, and then we would be going a distance of 2. And again, since we're going around the circle, that would take us a distance of 2 radians around the circle. So, to cut to the chase here, when we have theta as pi, change our thetas here. We were going vertically. Each step would be pi over 10,000 I. And we're doing that 10,000 times. Simple multiplication. We're going to go up vertically a distance of pi. Now, where does that bring us around on our circle? Well, that brings us 180 degrees around. And the point we end up on is basically your answer to this equation. So if we do it pi times, we've gone 180 degrees around the circle, and we are at -1. So I'm just going to finish up with a few more examples. So let's say theta was pi over 2. And again, we're going to say with n equals 10,000, just an arbitrary large number. You would have 1 plus theta over 2 over 10,000 I to the 10,000th power. And each of those increments is going to go up whatever theta over, pi over 2 over 10,000 is. And it's going to do that 10,000 times. So again, simple multiplication, 10,000 times 10,000. And you're going to go up a distance of pi over 2. On a circle, that would be pi over 2 radians. It's going to get you 90 degrees. The same thing's going to happen with pi over 4. Each increment that you go, each distance on this curve, right, and you're going to have almost an infinite number of points from here to here. The distance between them is always going to be, say in this case, pi over 4 over 10,000. And again, if we were to stack these vertically, the sides of this very small scale polygon here, you would go up a distance of pi over 4, which is 45 degrees around your circle, basically. And you would be going pi over 4 radians, which is your arc distance, and it's also your angle. So that would put you at radical 2 over 2 plus radical 2 over 2i. So hopefully at this point you understand why the value that we choose for theta determines how far we rotate around this unit circle when we're doing e to the theta I. It's important to have that understanding. And at that point, if you do understand that, this equation, e to the theta I equals cosine theta plus I sine theta, hopefully you've seen that before. But now hopefully that makes sense now. Because since we're just rotating some value around the unit circle, in radians, so like if we chose theta as pi over 6, so that you would be rotating pi over 6 radians around the unit circle, and that's just 30 degrees. Hopefully you understand now how it would result in this formula. Because all we're doing is we're getting the value in this complex plane at 30 degrees around a unit circle. And that's just basic trigonometry. The x value, or the real portion, is just going to be cosine theta because that gets you the adjacent side. And the opposite side is going to get you your y value, which is going to be sine theta. So this is just basic trigonometry and getting the value on a unit circle. And you don't need to know anything about e to the theta I to get a value on a unit circle. Again, it's just trigonometry. So cosine of 30 will get you radical 3 over 2. Sine of 30 will get you 1/2 or 0.5. But again, this is in the complex plane, so this is your real portion. So radical 3 over 2 is your real portion, and 1/2 is in the imaginary axis, so it's going up 1/2 I. And there you go. You have your complex number of radical 3 over 2 plus 1/2 I. So hopefully now you understand this. We've gone in depth about how rotating around this unit circle happens as we change the value of theta in e to the theta I. So you should have some idea how we end up here if we're doing pi over 6 as theta. That's just rotating pi over 6 radians around a standard unit circle. So we don't need to use a binomial or complex series to figure out what e to the theta I is. We could just use simple trigonometry. So again, hopefully now you get this. Maybe it makes more sense now. That was the goal of this video, and I hope it helps somebody. If not, sorry, I tried. But either way, hopefully you walk away with some more understanding. That's really it, and I want to thank you for watching the video and hope it helped. Thanks again.